Welcome to Paripurna Academy. Greetings to you, friends. Today's topic is elasticity and fluid mechanics. In this topic, we are going to discuss elasticity today. Before talking to elasticity, we have to discuss about strength of materials. Then afterwards, we will discuss about elasticity. What is strength of materials? It is talking about strength of particular material. Why should we talk about strength of materials? In our day-to-day life, we come across with different types of engineering products. All the engineering products are being made up of materials. So materials, we have ferrous materials, we have non-ferrous materials, composite materials, smart materials. The world is moving towards advanced materials, lightweight materials, in order to have sophisticated engineering products. So as a design engineer, we must know how to select the material for appropriate application. So it is mandatory to know about the strength of particular materials. How we can identify the strength of particular material? We have to disturb the material. How we can disturb the material? We have to disturb the material by applying the external load. So then only we can identify what is the maximum load that can be withstood by the material. So internationally, there is a procedure for applying the load. The testing name is tensile test. The tensile test, it is being done in universal testing machine. I will show you the testing method later on. Before that, let us discuss about some loading conditions. We have tensile load. Also, we have compressive load. Tensile load is nothing but two equal and opposite pulls. It will be acting like this. Compressive load is nothing but two equal and opposite pushes. Initially, we will discuss about tensile load and corresponding response from the material. Also, we will discuss about compressive load and corresponding response from the material. Let us take one material, cylindrical component. Say this chalk piece is in cylindrical in nature. The three dimension of this chalk piece is three dimension in nature. Let us take one metal of cylindrical component like this, and it is subjected to tensile loading. I already told you what is tensile load, two equal and opposite pulls. So this cylindrical component, it is cylindrical component, the cross section is circular cross section, and the diameter of this cylindrical component is D. Okay, and length of this component is L. So this is original length of the component. So now it is subjected to tensile loading. Why it is subjected to tensile loading? As I mentioned you earlier, we have to check the maximum strength that can be withstood by this material. So that's why tensile loading is applied. Now you have to imagine, okay, the material is subjected to tensile loading. What will be the response? What will be the reaction from the material side? The material will not be silent. Okay, for example, somebody is coming to attack you. Will you be silent? No. You will try to attack him, or you will try to protect yourself from that guy. Okay, the same principle applied here also. Okay, the material will produce equal amount of resistive force against this applied load. Okay, so here our objective is we have to increase the load until the material breaks into pieces. The load will be applied from the put value 0 to maximum value P. So like that we have to apply the load. Then only we can understand what is the maximum load that can be withstood by the material just before the breaking. Okay. So in between this 0 value to maximum load, what is the response of this material? What is the behavior of material? So that should be recorded. That should be discussed as a technical term. That is what we are going to do one by one. Okay. Now let us say it is subjected to tensile loading. Initially, the deformation will not happen because every cross section, every cross section of this material will try to resist this force. So to some extent, this resistive force from the material is equal to this applied load. So now that situation is equilibrium situation, no deformation, nothing will happen to this member. So considering equilibrium, now the material is in equilibrium situation. Under this situation, you can define what is stress. It is expressed as sigma. You can define stress. The resistive force offered by the material, the resistive force offered by the material against this applied load per unit area of the material is called as stress. Mathematically, it can be expressed as load over area. So this is the formula for finding the stress. Let me give you the detail for P. So it is equilibrium condition. So the applied load is equal to the resistive force. So it is applied load. Also, if this is equal to resistive force from material, like that, then A is nothing but this is the cross section. This is cylindrical component. So this is the cross section. So cross sectional area of the material. So like that, we discussed about stress. Now you have to imagine the load is continuously being applied on the material. Okay. So now I hope you understood about stress. Now let us discuss about strain. If the load is increases further, what will happen? What is the behavior from the material? To some extent, the material will produce the resistive force. But our objective is we have to increase the load until the material breaks into pieces. Now, the resistive force, the material cannot able to produce the equal amount of resistive force. It will surrender to the applied force. So deformation begins. So the deformation will be like this. Let us say this deformation is del. Under this phenomenon, we can define strain. Strain, the notation is E small e. So strain can be change in length over original length. So here change in length, the unit is meter or millimeter. Length, the unit is meter or millimeter. So it has no unit. It has no unit. So strain, how you can define now? The ratio of increasing length over original length is nothing but strain. So it has no unit. Whereas stress, already we have seen, stress, the notation is sigma, it is load over area, and load, the unit is Newton, and area, the unit is mm square. So the unit of stress is equal to Newton per mm square. So now I hope you can understand what is strain. So for every increase in load, what is the behavior of material, and we are obtaining some technical definition. This is how this session will move on. Okay. Now we will discuss about tensile stress, tensile strain. See, so this is cylindrical component. Again, it is subjected to tensile loading, two equal and opposite pulls. So tensile, this magnitude P, this magnitude P, both are same. Two equal and opposite pulls. This cylindrical component subjected to tensile loading. Now, what is the stress? The stress induced in every cross section of the material is tensile stress because this is tensile loading. Now, if you want to give mathematical expression for tensile stress, sigma subscript T, and this should be tensile load. This should be tensile load and cross sectional area. Cross sectional area of the material. So, like that, you can define tensile stress. The load is P subscript T. This is cross-sectional area of the material. So like that you can define tensile stress. Now coming to tensile strain. Okay, so here the load is tensile load. Because of this load, this much deformation taken place. The increase in length is del L. So the tensile strain, the notation is E, and E subscript T is nothing but tensile strain, which is increase because of the tensile load. The length is increase in length over original length, which is del L over L. So it has no dimension. So this is how you can define tensile strain. The tensile strain is nothing but the length is increasing. This is say this is axis of the cylindrical component. The length is increasing along the load direction, along the line of action. So this is tensile strain. You can give another name also for this strain, which is linear strain. Linear strain. Okay. This is how we can discuss tensile stress and tensile strain. Now we will discuss about compressive load and what is the behavior of material. Let us discuss and let us obtain some definition. Okay, the same cylindrical component let us take, and it is subjected to compressive loading. Compressive loading is nothing but two equal and opposite poles. So this is original length. L is original length. Original length of the specimen, and this is diameter. D is nothing but original diameter. Original diameter. Now what will happen because of this compressive load? What will happen? As I already mentioned, the material also will try to produce some resistive force. So to some extent, the resistive force from this material will be equal to applied load. Under this situation, you can define the stress. The name of the stress is compressive stress. Okay, sigma subscript C, which is compressive load. Compressive load over cross-sectional area. Of the material. And here the unit is Newton per m1 square. This is how you can define the compressive stress. Now let us discuss about compressive strain. Let us discuss about compressive strain. For this compressive loading, once the material is surrendered to the applied load, deformation will begin. So for this compressive action, the length will decrease, the diameter will increase. Okay, so the diameter will increase like this. So this is nothing but del L. Okay, the length is decreased. This is the original length. Del L length is decreased because of the compressive load. Now, what is compressive strain? The notation can be small e subscript c, and this is compressive. Sorry, decreasing length. Decreasing length over original length. So this is also decreasing length also represented by del L over L, and it has no dimension. So this is how we define compressive strain. Now I hope you must know what is stress, how we obtain stress in equilibrium situation, then what is strain. Then what is tensile stress? What is tensile strain? Similarly, what is compressive stress? What is compressive strain? Already we have discussed. Okay. Now at this point of the time, we can discuss longitudinal strain. What is longitudinal strain? And what is lateral strain? Lateral strain. You take any example, whether compressive loading or tensile loading. Now, in our board, compressive loading picture is there. Let us take this example itself. Okay. What is longitudinal strain? Okay. The strain along the line of action of the load. So, for example, here the length is decreasing along the load direction. So that strain is nothing but longitudinal strain. At the same time, simultaneously, indirectly, the diameter is increasing perpendicular to or right angular to the line of action of the load. So that strain is lateral strain. So this, I hope you understood what is longitudinal strain and what is lateral strain. Let me explain with tensile loading condition. Say this is cylindrical component and it is subjected to two equal and opposite fluids. Okay, so this is original length of the specimen and this is original diameter. Because of this tensile loading, the length will increase and this is changes in length. Now, how you can define longitudinal strain? See, the length of the object is increasing along the load direction, along the line of action of the load, or along the axis of the member. This is nothing but longitudinal strain. The another name for longitudinal strain is linear strain. Linear strain, you can say tensile strain. Tensile strain. Okay, for the same loading condition, this diameter, if the length is increasing means the diameter will decrease. This is original diameter, the diameter will decrease. This is nothing but d minus LD. So the diameter is decreasing right angle to the line of action of the load. So that is lateral strain. Okay. This is how you have to define what is longitudinal strain, what is lateral strain. Now you can discuss about Poisson's ratio. Poisson's ratio, it can be represented as mu or 1 by m. So just now we have discussed about lateral strain and longitudinal strain. It is the ratio between the lateral strain to the longitudinal strain. And from this equation, okay, calculation of longitudinal strain or direct strain, linear strain is easy. Lateral strain, through this formula you can calculate. Lateral strain is equal to Poisson ratio, the product of Poisson ratio into longitudinal strain. Okay. This is how you can calculate lateral strain. Now what is Poisson ratio? It is the ratio of lateral strain to the longitudinal strain, which is constant for the given material within elastic limits. So this is nothing but Poisson ratio. Okay. Now we are coming to the topic, elasticity. Elasticity is nothing but it is a material property. Okay, so we have taken cylindrical component and the load is applied. This is example for tensile loading. Okay, if the load is increasing, the deformation will increase. It will deform like this. It will deform like this. Okay, immediately if the load is removed, the deformation will vanish. The material will bounce back to its original shape and original dimension. That capability of the material is called as elasticity property of the material. Okay. If the load is removed suddenly, in fact, our objective is we will keep on increasing the load until the material breaks into pieces. Okay. But suddenly we have to analyze for every situation. If the load is removed, how the material will behave. That also we have to understand. Okay, that's what. If the load is removed suddenly, the deformation, the changes in length, it will vanish. It will bounce back to the material will get its original shape, original dimension. That capability, that property of the material is nothing but elastic property. Whereas we can discuss about plasticity. Okay, plasticity also another material property. Okay, let us consider this example. If the load is increased further, okay, and material is deformed like this. Now, if you remove the load, this deformation, this much deformation, okay, the material cannot able to recover its original shape. The deformation will be permanent, which means plastic deformation taken place. So that property is nothing but plasticity or plastic property of the material. The meaning is if the load is removed, the deformation will not vanish. The deformation will be permanent. So this is del L. This will be permanent. Yeah, the material cannot able to recover its original shape. So this property is nothing but plasticity of the material. Okay. Now you understood about elasticity. Let us discuss about Hooke's law. Hooke's law. Uh, it states that stress directly proportional to strain within elastic limit. Within elastic limit. Okay. You can remove this proportionality by introducing the constant E. Okay. So E is nothing but it is a material property which is called as Young's modulus. Young's modulus or modulus of elasticity. Or the another name is elastic modeling. And from this you can define the Young's modulus. Okay, it is stress over strain. Okay, so how you can define Young's modulus? Young's modulus, the stress is, the unit is Newton per mm square. Strain has no unit, so Young's modulus, the unit is Newton per mm square. The ratio of tensile stress to the corresponding tensile strain or compressive stress to the corresponding compressive strain is nothing but Young's modulus. This is material constant. Okay, and Hooke's law, I hope you understood clearly. Stress directly proportional to strain within elastic limits. Now, let me explain about shear stress. Previously, we have discussed about tensile loading and corresponding tensile stress, and compressive loading corresponding compressive stress. Now, let us discuss about shear stress. Shear stress, the notation is tau. Okay. To explain shear stress, let me give you one example. Okay. So this is one metal plate, upper plate. This is one metal plate, and this is another plate. This is lower plate. Okay. First, let me explain. Okay. We are going to join these two metal plates together with the help of rivet. Rivet is nothing but our belt buckle is there, right? Belt buckle, it is being attached with the leather with the help of a small rivet pin. In the same way, this two metal plate, it should be permanently joined with the help of this rivet. If we give some force over here with the help of hammer, okay, it will join together. Say for example, this metal plate, it should be joined together for making table, okay, the rigid table purpose, like that you assume. For that, this operation is being done, okay. So now, coming to our topic, shear stress. Okay, shear stress is nothing but tangential force, equal force, magnitude force, which are applied tangentially across the resisting section. In this case, this is the resisting area section. This is the resisting area which resists the shear force. It resists the shear force. Okay. Now the metal plate, upper plate, it is applied with the tangential force P, shear force P like this, and lower plate, okay, the force is applied like this. Okay, you should not confuse while discussing tensile stress. This is same cylindrical member. The load is applied like this. This loading is tensile load, but this loading is different. Okay, one force is applied on the upper plate, another force is applied on the downward plate. Okay. Now, what is your imagination for this loading purpose? How the failure will take place across this resisting section? This is the rivet member. Okay. This rivet member, this section, it is circular cross section. The rivet section is circular cross section, and the diameter is D. For this loading condition, how the failure will take place? What is your imagination? So, okay, this resisting section will be sheared off like this. See, will be failed. Nothing will happen on this metal plate. Okay, whereas tensile loading, the length will increase. But here, in this plate or the lower plate, nothing will happen because the shear force it is okay occurring failure across the resisting section. Resisting section is there in the rivet, so it will be sheared off like this. Now coming to shear stress down, it is shear force over area of the specimen. Okay, so we already discussed stress is equal to load over area. Similarly, here shear stress is equal to shear force or shear load. Okay, shear load. So that is nothing but P. And the area of the specimen. Here, this is the rivet specimen is the area you have to consider. This area is cross-sectional area is circular diameter. So pi by 4 d square. Okay, if you apply the area value here, this is P over pi by 4 d square. Finally, shear stress equation is 4P over pi d square. This is how you can calculate shear stress. Now, definition for shear stress is two equal force, magnitude force, okay, acting tangentially across the resisting section. As a result of this tangential force, shear force, the material will be sheared off across the resisting section like this. Okay, so this is example for shear stress. I will give you one more example for shear stress. Let me give you one more example for shear stress and the corresponding shear strain. Okay, consider a rectangular block. Right, consider a rectangular block. Okay, of height L and length L. Okay, the width of this rectangular block is unity. Okay, and this AB end is fixed. Okay, now let us say the shear force is applied on the top surface, CD surface of this rectangular bar. Okay, what will happen since this AB end is fixed? This end also will experience the same magnitude of shear force, but in the opposite direction. Okay. Now this block, rectangular block, it is subjected to shear force. One force is applied on the top surface. I mean on the CD surface. Okay. So if this surface is experience this force, since this AB end is fixed, this AB end also will experience the same shear force, same magnitude in the opposite direction. Now you imagine because of this loading condition, okay? So because of this loading condition, right? So it will move like this. It will deflect. It will deflect like this. Okay. So because of this shear force condition, D point will be deflected to D dash, and C point will be deflected to C dash. The block it will be shifted to this much angle. This angle is nothing but shear strain. Okay. So now we can calculate the shear strain value from this geometry. Here, this is the deflection, this is the deformation. DL is transverse displacement by S shear strain. Okay. From this triangle, ADD dash, from this triangle, tan pi is equal to opposite side over adjacent side, and which is tan pi equal to opposite side is equal to DL and adjacent side is equal to height of the block, which is tan pi equal to DL over H. Okay, here since the theta is very small, tan pi is approximately equal to, okay, pi. So pi equal to dl over h, shear strain. Okay, so this is how we can obtain the shear strain value. So now let us discuss about stress strain curve for ductile material. Okay, so this is the stress strain diagram for ductile material. In x-axis, strain is being taken, and in y-axis, stress is being taken. I mean the load is being applied, and here the strain or deformation, it is being taken. Here the strain is independent variable and stress is dependent variable. Okay, if you look at the curve from O to point O to A, the curve is straight line, which means the stress proportional to strain. For any increase in load, the strain also will increase. So Hooke's law applicable within this range. O to A, it is a straight line. So stress proportional to strain. Okay. The stress at point A is limit of proportionality. Stress at point A is limit of proportionality. If you increase the load beyond point A and until point B, okay, still the material will behave like elastic material. Now, if you look at the curve is not a straight line; it is a non-linear curve. Okay. Now, here we are facing the little controversy. Okay, the material will behave like elastic material until point B. But what is Hooke's law? Stress directly proportional to strain within elastic limit. But if you consider the curve from A to B, it is non-linear curve, but the material is behaving like elastic material until point B. So here the controversy is coming for Hooke's law. Let me give you the explanation. Okay, for metal like steel, in practical application, this non-linear portion is very small. So altogether it is ignored, it is neglected, and it will be treated as straight line. That's why in definition Hooke's law states that stress directly proportional to strain within elastic limits. Okay, so if you increase the load beyond point A until point B, the material will behave like elastic material. Okay, the stress at point B is nothing but elasticity. If you increase the load, okay, from point B beyond point B, if you increase the load for any small increment in load or almost for the constant, see, this is the magnitude of the load. This is the magnitude of the load for this condition. Okay, for constant load or small increase in load, there will be a considerable deformation because the material is already severely stressed. Now you should remember, okay, tensile load. So it will increase, the load will increase until the material breaks into pieces. Okay. So this is how the material will be tested for identifying the strength, and from that this particular result, the stress strain curve is being obtained. Okay. So now already the material is severely stressed, severely loaded. We are increasing the load. Okay, in order to finding the behavior of the material. So it is already severely stressed. So for the constant load or small increase in load, there is a considerable deformation. Okay, so the material is behaving like plastic material. Okay, this is plastic region. Okay, and stress at point C is upper yield point. Upper yield point. Okay. Now, if you look at the curve is coming down. I mean, the load is decreasing. Why the load is decreasing? Because the material is already severely stressed. The material realizes that somebody is attacking me, somebody is killing me. Okay, I am getting tired. So you need now under this situation you need not increase the load. Okay, so before the application of the load, the material yields by itself because of the previous loading. So that's why the load is decreasing and the deformation suddenly stops at point D. So the stress at point D is lower yield point. Lower yield point. Okay. Now at this particular point, again the curve is increasing, which means okay, the load is increasing. Why? Because the material realizes that somebody is disturbing me, somebody is going to killing me. I have to oppose, I have to gain back my energy, I have to oppose the applied load. Okay, like that the material is imagining. Okay, like for example in wrestling game, okay, one person he is beaten his opponent person and that person is down, but he is trying to gain back his okay energy in order to attack him. Like that the situation for material is here. So at point D the material is realizing, okay, I have to gain my energy. So this is what happened. The material gains enormous energy back at point D. So now what is the situation of this applied load? The applied load, it should increase. That's why suddenly the material applied load also realizes, okay, the material getting energy back, so I have to increase the load. Okay, so the load is suddenly increasing and it reaches point E, so which is nothing but ultimate stress. The stress at point E is ultimate stress. Ultimate stress. And at this point, the neck is formed. Okay, neck is formed means the material, okay, for this loading condition, like this, okay, the neck will be formed after point E and it failed at this one. The stress at point F is failure point. Failure point, like this. Okay, so this is nothing but neck. Neck diameter. So this is how we have to explain, we have to understand stress strain curve. Okay. Now if you draw this slope, okay, in this straight line, and you can define the Young's modulus rise over run, which means rise means stress direction, run means deformation direction. Young's modulus is stress over strain. Okay. So if you draw the curve area under this curve, area under this stress strain curve. Okay, this is triangle. Okay, what is the formula for triangle? So this is stress is nothing but load and strain is nothing but del L. Okay, so this is nothing but strain energy U. Okay, the triangle formula is of, okay, P delta L. This is how the strain energy. If you apply the load, the energy will be stored in the material. That energy is, okay, strain energy, and 1 by 2 P delta L. Okay. Here, instead of P, you can use this relation. Stress is load over area. From this, load equal to stress into area. Okay. So, instead of P, you can substitute this value. Similarly, del L. You know strain is equal to change in length over original length. Okay. So, instead of del L, you can apply strain times length. Okay, now you substitute P value and del L value in this strain energy equation. This will become 1 by 2. Instead of P, it is sigma times A. Instead of del L, this is strain times L. Okay, now just you rearrange this equation. U equal to 1 by 2 sigma E, stress in the strain, and AL together. AL is nothing but area of the material and length of the material, which gives volume. Okay. Now U equal to 1 by 2 times stress into strain into volume. Okay. Now this area gives, okay, energy stored. Energy stored in the material. Energy stored in the material per unit volume. Per unit volume. So this equation, you can bring this volume this side. Okay, this is, so this will be 1 by 2 stress times strain. This is the, yes, strain energy stored in the body. Okay, during the tensile test. Okay, so this is the measure of toughness of the material. This area gives the measure of toughness of the material. If the material is tough enough, maximum load is needed for failure of the material. So elastic material, it is widely preferred for making the all engineering components. From this stress strain diagram, we can draw some formulas. Let me give you the formulas. Okay. So because it is subjected to tensile loading, so the length will increase. So you can calculate percentage elongation by using this formula. Increase in length over original length times 100 will give percentage elongation. This is first formula. Second formula, okay, percentage reduction in area. If the length is increasing, you know this is cylindrical component, diameter will decrease. So you can calculate percentage reduction in area, which is pi by 4 d square minus d dash square divided by pi by 4 d square. Here you can cancel pi by 4 and d, small d is nothing but original diameter of the specimen. Okay, so say this is original diameter and load is applied, tensile load is applied like this. Finally, it will be like this. After the failure, it will be like this, and this is nothing but d dash, neck diameter. So d dash is nothing but neck diameter while the breaking of material taking place. So now you can cancel pi by 4 value. So percentage reduction formula is d square minus d dash square divided by d square. Okay, times 100. Percentage reduction in area, right? Then another formula is you can calculate safe stress. What is safe stress? That is the value you can operate the material without fail. Okay, if you operate the material or any product, okay, beyond the safe stress, failure may occur. So for that purpose, it is required to calculate safe stress before the product is being manufactured. Okay, it is the ratio of yield stress over factor of safety. Okay, at this point, factor of safety is nothing but the ratio of ultimate stress over permissible stress. You may call it as permissible stress or operating stress or working stress, whatever it is. So this is the definition for factor of safety, and from this equation you can calculate safe stress. Okay. Now if you want to calculate stress at elastic limit, any stress means load over area. So here you are going to calculate stress at elastic limit. So load at elastic limit over cross-sectional area. Similarly, here if you want to calculate stress at ultimate limit, this is load at ultimate area, okay, ultimate limit divided by area. By using these formulas, you can calculate the problems related with stress strain curve. So we have to discuss a few more definitions. Okay, I thought of giving you this definition. Now let us discuss that one. Volumetric strain. Okay, volumetric strain means if you consider the object in 3 dimension, for because of the applied load, the entire volume. Okay, previously we discussed about length is increased, diameter is decreased, like that. Okay, if you consider the other dimension, volume, the entire volume also will change. So volumetric strain, it is, the notation is E subscript V, which is change in volume over original volume. Using this equation, you can calculate volumetric strain of the particular object. Okay. Then coming to bulk modulus, it is represented as K, and it is the ratio of direct stress to the volumetric strain. And the equation is direct stress is sigma over, okay, volumetric strain del V over V. Okay. By definition, bulk modulus is when an external force is applied on the material, okay, three mutually perpendicular direct stress is acting on the material, 3-dimensional material, then that situation, the ratio of direct stress to the corresponding volumetric strain for the material, given material within elastic limit is constant. That is nothing but bulk modulus. So using this relation, you can calculate bulk modulus value. Okay, and Young's modulus value in terms of bulk modulus, it is given as Young's modulus E equal to, okay, in terms of bulk modulus, it is 3K times 1 minus 2 mu. Mu is nothing but Poisson ratio, and from this relation you can obtain Poisson ratio value like this, 3K minus E divided by 6K. K is nothing but bulk modulus, E is Young's modulus. Okay, and one more term we have to discuss. We already discussed about Young's modulus. Okay, Young's modulus is considering tensile stress and compressive stress. Okay, here we have to discuss about modulus of rigidity. It is represented as C or sometimes G or N. Shear stress directly proportional to shear strain within elastic limits. Okay, so you can remove this proportionality by introducing the constant. That constant is nothing but modulus of rigidity. Tau is shear stress and phi is shear strain. And from this equation, shear stress over uh, shear strain is equal to modulus of rigidity. The unit is Newton per millimeter square. Okay. So normally in strength of material, the unit will be maximum millimeter, because the deformation it will take place for very minute cases only, micron level changes. Okay, but whereas that's why we are using millimeter unit. Whereas in fluid mechanics, for example, fluid transportation system, the fluid should be transported through pipelines for 1 kilometer, 2 kilometer, 3 kilometer. Okay, in that case, meter unit, if we say the unit in meter, say 1 meter pipeline, so physically 1 meter is this much. We can recognize easily, we can imagine easily, this is 1 meter. Okay, instead of meter, if you say okay, we cannot physically recognize. That's why in strength of material, the unit will be in in fluid mechanics, it will be in meter. Like that, it will be there. Okay. Now let me explain uh, how the tensile test apparatus will be there, and how it is being displayed. Okay, so this is a universal testing machine. Okay, it has movable jaw and fixed jaw. In between movable jaw and fixed jaw, the component will be placed like this. Say this is tensile loading, right? This is tensile loading. Okay, so in between fixed jaw and movable jaw, this specimen will be placed. So the movable jaw will move along with the specimen. I think in that picture the specimen is clearly fixed in between movable jaw and fixed jaw. So if the movable jaw is moving along with the specimen, the meaning is load is applied, so the length will increase. Okay, and the load will be applied from the tool value 0 to maximum. Okay, uh, so this is the figure. See, universal testing machine. It is clearly visible, and specimen also visible. Okay. So this is ASTM standard specimen. Okay. If you want to conduct the tensile test, I mean, if you want to identify the strength of particular material, we know you have to apply the load. Okay. For that, the specimen should be prepared based on this dimension. Okay. Then it will be placed in between the universal testing machine, and the load will be applied. So now let us discuss about stress strain curve for ductile brittle material. Previously we discussed about stress strain curve for ductile material. Now we will see the stress strain curve for brittle material. Okay, the strain is taken in x-axis, and the stress is taken in y-axis. Okay, if you consider the curve from O to A, the curve is straight line, which means like ductile material, stress proportional to strain within this limit. Stress proportional to strain within this point. Okay. Afterwards, if you increase the load beyond point A, the curve is non-linear and it is getting failed immediately. At this point, it is getting failed immediately because it is not elastic material, it is brittle material. Cast iron is example for brittle material, glass is example for brittle material. So that is the reason brittle material will not be preferred maximum for making engineering products. In fact, it is being used in many engineering products, but elastic material is widely used for making engineering products. Okay, you can compare the stress strain curve for elastic material, they are ductile material and brittle material. Okay, and you can identify elastic material, what is the maximum strength, where the failure occurs. Similarly, brittle material, okay, it is immediately failed, so we should not prefer brittle material. Okay. So for ductile material, if you prefer the life of the engineering product will be longer. Like that you can understand and you can prepare. So now let us see one simple problem related with stress and strain. A rod of 150 centimeter long and diameter 2 centimeter is subjected to an axial pull. Okay. What is tensile load? Two equal and opposite pulls. So axial pull means tensile load. It is 20 kilonewton. If the modulus of elasticity of the material of the rod is 2 into 10 power 5 Newton per mm square, determine the stress induced in the material, the strain induced, and the elongation of the rod. So this problem we have to solve. Okay, a rod of 150 centimeter length. So this is the cylindrical rod of length 150 centimeter, diameter 2 centimeter. Okay, and it is subjected to axial pull of 20 kilonewton. So length of the rod is given L equal to 150 centimeter, and the diameter of the rod 2 centimeter, axial pull is given. Okay, so what you have to calculate? Stress you have to calculate, strain you have to calculate, elongation of the rod you have to calculate. Okay, so now what is the formula for stress? Stress load over area. Okay, so here what you have to understand, Young's modulus value is given in Newton per mm square. Okay, while calculating stress value, okay, you are going to apply area value also. Okay, if the area value also in millimeter, then the unit must be similar. Okay, while substituting the value, the unit must be similar. For that, the diameter value is given in 2 centimeter, you convert into millimeter. 2 into 10, it is 20 millimeter. Now you calculate area of the rod A, which is 5 by 4 d square, 5 by 4 20 square, which is area of the rod is 314.159 mm square. Okay. Now if you calculate stress value, stress is equal to load over area. So load is given axial load 20 kilonewton. So 20 times 10 power 3 Newton. Okay, divided by 314.159 millimeter square. Okay, so the stress unit is Newton per millimeter square. Now you completed stress value. Okay, now second question, strain you have to calculate. Okay, so strain, the equation is stress over Young's modulus. Okay, you know stress directly proportional to strain. Okay, stress equal to Young's modulus into strain, and from this what you have to calculate? Strain equal to stress over Young's modulus. This is how we obtain this equation. Now stress value already we calculated 63.66 Newton per mm square. Substitutes value here, and Young's modulus value is given in problem. See now it is applied here 2 into 10 power 5 Newton per mm square. So now this unit and this unit is similar, you can cancel, and this is the value of strain. Strain means this much strain deformation taken place because of this 20 kilonewton load. Okay. Then the last question, elongation of the rod you have to calculate. Elongation means del L. Okay. Strain, we have this formula also, change in length over original length. From this formula you have to calculate del L. It is the product of strain times L. So using this formula, you can calculate the del L value. Length is 150 centimeter and strain value is this one. If you multiply these two values, you are getting del L as this one. Okay. So using the formulas. Okay. So far we discussed about stress, types of stresses, tensile stress, compressive stress, tensile strain, compressive strain. Okay. Then longitudinal strain, what is lateral strain, what is Poisson ratio, what is Hooke's law, what is Young's modulus, what is modulus of rigidity, what is factor of safety, bulk modulus, volumetric strain, then some formulas in stress strain curve. Okay, everything we have discussed. By rearranging those formulas based on the requirement in your problem, you can calculate any problems under elasticity property. Okay. So I hope I explained you in a simple way. It is easy to understand this elasticity concept. You try more problems for solving symbols, stresses, strain, elongation. Okay, small twist may be given in the problem, but you can use this formula and you can solve the problems under elasticity. Okay. Thank you.